work in Geoscience Australia's Digital Earth Australia program. And we're going to take a bit of a change from what we've done this morning because we're actually interested in the surface of the Earth. So for us, cloud and aerosols are actually noise, so we throw those out because we want to know what's happening on the surface of the Earth. So just by way of introduction, Digital Earth Australia is both a database and a data set. So we have a Landsat and Sentinel-2 data that are freely available and open from the USGS and the Europeans, and we use that, grab that data, correct it, take out the aerosols, take out the clouds, or at least put a mask for the clouds, because sometimes we don't actually need to take the clouds out. And we grid it so that every pixel sits on top of every other pixel. So then what we can do is drill through time and get, for a single location or for an area, how that has changed through the satellite archive. And so when I say that we're a platform and a data set, the actual database that Digital Earth Australia sits on is open source. And so we have databases around the world where they have themselves referenced their own satellite archive. Digital Earth Australia has the Australian Landsat and Sentinel data. And because we've created this analysis-ready data set, what it allows us to do is create algorithms that can automatically process big volumes of data. So this is all housed on the NCI in collaboration with the NCI. And so we've got access to the compute and the data in the same location so that we can start to process vast quantities of data very quickly. So I didn't want to get too much into the detail, but I just wanted to use this time to show you some of the things that we're doing. So I'm going to demonstrate very quickly a number of the products that we've already released using, based off that Landsat archive in particular. The Sentinel archive was only made public about a month ago. It's quite new. So we haven't put our product suite onto the Sentinel archive yet, but that's something that'll come later on. And then I also wanted to show you some case studies. So these are not products that we've developed, but it's just showing you the power of having a Python-based API that allows you to write algorithms that can do things really quickly. If you want any of the detail about any of these products or case studies, come and talk to me afterwards. Otherwise, all the products are available now on National Map. And if you want more info, you can go to our website and there's a product page that has links to publications and things. So the first product that we released is something called Water Observations from Space, or WOIS. And what this is an Australia-wide analysis of whether a pixel is wet or not. And so what we have here is for all of Australia, the percentage of time from 0 to 1, or 0 to 100, that a pixel was wet. And so what you see is that areas that are red were wet less of the time. And so what you can see popping out here are some of those floodplains that will flood in large rain events, but that actually are not usually wet. And so when you zoom in, what you can see is the behaviour of water in the landscape. And so we can do this stacked through all time, which is what we have here. But for every Landsat scene, we actually have that same classifier that we apply over it. So for every Landsat pass over Australia, for every pixel in that scene, we have a classifier that says, is it water, is it not? And that becomes really powerful, and I'll show you an application that we've recently developed later on where we use that product. The intertidal extents model. So the problem that we have with intertidal zone is that we don't have a lot of observations. But what we can do is use Landsat to derive the intertidal zone for Australia. So what this particular product does is uses Landsat and a tidal model to find the Landsat scenes that correspond to different tidal heights. And what it then does is take an average of what the coastline looks at those different tidal heights and bins it. So to explain what that means, for this picture here, areas that are red are land only 0 to 20% of the time. And so you can get an idea that those are the really low tide, the parts of the landscape that are exposed at low tide. Conversely through to the sort of yellow and then through the greens and the blues, which means that they're mostly exposed and only at the very extreme high tide do they actually inundate. What you can then do is use that image, that data, to produce these composite images. And so on the left you've got a high tide composite, and on the right you have a low tide composite. And what this is it takes all of those that data set that tells you when the high tide was and when the low tide was, and it creates a picture that gives you the average conditions at that time. And so you can see on the left, you have a picture of what Australia, or this part of Australia, would look like at high tide, and conversely, low tide on the right. So we've recently taken this product one step further. So we had our tidal models and our percentiles, our binned data for our tidal zone. What one of my colleagues has done is actually take that data and then correspond it to LiDAR passes. So we have some LiDAR data for Australia. We don't have a lot, but what we do have, we can use by knowing what the tide was at the time that that LiDAR pass was taken. And what this allows us to do is actually quantify the tidal zone. So this is just an image to show, and you can see that the vertical resolution is quite exaggerated, but what this shows you is a quantitative picture of what the tide, the intertidal DEM actually looks like, what the bathymetry, the elevation of the intertidal zone is. And so this provides us with that gap in knowledge. So we know what the elevation of the land is, and we know what the elevation of the ocean is. This fills that gap and provides us the elevation of that intertidal zone. So this is another product that has been released. I can get my thing to play. And what this is, so before I explain the mangroves product, I just want to quickly talk about what's flashing up here. This is the power of Digital Earth Australia. This is every cloud-free observation of this particular location back to 1987. And so what we can then do is pull out only the ones that we want, so we didn't want cloud in this case, and you can start to see changes through time. And so superimposed on that here is a classifier that finds the mangroves. So it uses the 10th percentile of, sorry, the 90th percentile, 10th and 90th percentile of NDVI to define where the mangroves actually are. And what you can see through time is how those mangroves are changing. So the mangroves are classified into different canopy densities, and what you'll notice is that in here, if I can get my mouse back, here we go, is here the mangroves are growing up through time, and if you notice just here, there's going to be a massive die-off event, and the mangroves are all going to disappear. So what we can actually do is for mangroves, we can look at how they change through time, and we can start to quantify and look at the thickness of Australia's mangroves. And so this particular plot does exactly that. So it bins the Australian coastline, and for every bin, there's a corresponding plot. And what these plots show you, the total height of all of the colours is the amount of mangrove. The darkest green is the thick mangrove, the closed forest mangrove. The medium green is open forest. And then the lightest green is woodland, or sort of very sparse cover. And so what you can see is that over time, the relative amounts of these different canopy densities changes, and also the total amount changes. So, where's the good one? Here. So you can see here, the actual total amount of mangroves is increasing here. And then what you see is that here you've got a dip in the mid-range, the open forest mangroves, and a corresponding increase in the closed forest. And what you can actually see, if you look at particular areas like where a tropical cyclone has gone through, that the dense canopy decreases and the open forest and woodland canopy increases, because those mangroves have actually been impacted by that cyclone. So that was just a really quick overview of some of the products that we have available. So they've already been published and are available via National Map to look at. If you would like to access that data, it's all sitting on the NCI, and we can talk later about how you can get access to that. What I now want to talk about is some of the kind of case studies where we haven't published a product, but we've just demonstrated some of the capacity and what we can do. And all of our code, if you want to access and do the same kind of analyses, is available on our GitHub page. So we were asked by a stakeholder to help quantify the effect of environmental flow on marshland, on wetlands. And so what you can see here on the left is a false colour image where you've got the sort of brighter green of vegetation, and this colour here, this sort of dark black, dark blue, is actually open water. And here on the right you have a corresponding time series. And so what you can see is that as this environmental flow comes in, and it's going to pop in about here somewhere, that you can actually see a corresponding flush of water and vegetation. So it's a bit hard to sort of pull all of that together in this plot. But when you turn that into a time series, it becomes really clear the impact this water is having on this ecosystem. So this is for this particular sort of red polygon here, the Hattar Lakes. And what you can see here in this light blue strip here is the wet vegetation. So this isn't open water, this is just kind of mushy vegetation. And we use a tassel cap wetness indice to get to that. And then we've got our surface water here, which is the WOIS classifier I talked about before. And when you put them together, you get an indicator of how wet this area is. And what's really interesting is that when you plot the occurrence of environmental flows on this axis, you can actually start to see the impact that those environmental flows are having on this ecosystem. So you can see here, it was almost completely dry until this particular event came through, and we get a large response down here. And you can see sort of the same kind of thing happen here. You've got a big environmental flow that comes through, and then a big response. So it helps us to actually start to quantify some of the things that we've really kind of known in an arm-wavy way. This is the same kind of analysis, but this is done using just a specific vegetation type. So this is the common reeds community in here. So we use the Living Atlas of Australia to find the polygon for that, which is here. And so now what you can do is, rather than the entire wetland, you can look at the impact of that environmental flow on just one particular community, or at least the location that that community resides in. And again, you can see there's this large natural flow event here, and then some smaller environmental flows here that correspond to a big wetting in this particular area. Another thing that we're actively working on is groundwater dependent ecosystems. So we want to know where our natural springs are, where is the vegetation getting its water source from groundwater, because potentially these become areas that can be, we know that there's a natural water source there. So what this map here is for all of Northern Australia north of the Tropic of Capricorn, because that's the area that we were interested at this time. What you can see here is the percentage of time that every pixel was observed as wet. And what you see pop out are some of these natural springs or groundwater dependent ecosystems. And if you zoom in, you can actually see here, we have a spring that's been mapped here. And you can see the corresponding dark blue, which was open water. And if you actually go out there, that's what you see. So we're able to actually map these things from space. And we're trying to do that for all of Australia. So the more I work in this field, the more I realise that the data sets I thought we had, we actually don't. And one of those that I thought we would have, but that we don't, is where is Australia's persistent water? So where do we know that there is going to be standing water in the landscape? So this is the product that we developed to try and help with that. So you can't really see it on this side, but I just put it here for context. So this is New South Wales. And what you probably can't see, but you may see, is a smattering of dots. And what those dots are polygons that draw around the maximum extent of water bodies for all of New South Wales. And so what we now have is a polygon data set that we can use to go back through time. So the same way I was saying that you can take a pixel and draw through time through the archive and get every observation for that pixel, you can take a polygon and do the same thing. So just to show you what that looks like in this kind of blobby bit down here, what you can see is that we actually start to pull out, so these are some natural lakes. And in here, again, you probably can't see it, but it's actually a very L-shaped structure. And this is a man-made dam, an on-farm storage. And in this particular study, that's what we were targeting, were these man-made storages. But you can actually see as well, things like the river are popping out. Again, just in this part here, where we have a lot of on-farm storages, you can see that it's picked up really nicely in this data set. And you may not be able to see it, but again, the structures are quite square, so we know that they're going to be man-made. So now that we have a polygon data set for every persistent water body, in this case in New South Wales, but in the future for Australia, what we can do is start to treat that as a whole. So rather than dealing with pixels, we start to deal with objects. And so for this object here, for example, what we can see here is that it's all really nice and dark blue. And so we know that that is a full dam. The one thing to note is that because we're using earth observation data, we can't get volume. We are only looking at surface area. If we want to get volume, we have to have some kind of information from LiDAR or some observations on the ground to supplement this. But what we can do is look at the change in surface area. So this one in the middle here, where you can kind of see this little squiggle of cyan here. What this is a dam that has maybe 10 to 20% water in it, maybe up to 40%. And then the same water body here is empty. And so what we can do is look at this through all of time to see how each water body is changing. What that allowed us to do is to produce a current drought snapshot. So this is a product that we pulled together at the request of a stakeholder. We were already working on the sort of water body polygon drill, and they said, hey, we really need some help. Can you help us find out what the drought's like? I said, yes, we can, we've got the product for you. And so this is something that we pulled together based off that in less than 2 weeks. And again, it's a bit blurry, but what you can see here is these big areas of red up here, which says that the water body that at some point in the last 18 years was full, is now empty. And down here, it's a bit lighter, so we've got a bit more water in the this Murray area down here. We've done the same analyses for 2017 and the same analyses for 2016, just to get an idea if this red is alarmist or if it always looks like that. In 2017, it looked much the same. It was a little bit greener through here. In 2016, the map was almost entirely green and blue. So in 2016, we know that these water bodies did have water in them. So I've just done a bit of a zoom, and I'm sorry, again, you won't be able to see much of this, but you can start to see that these polygons, when you actually sit them into the landscape, start to make a lot of sense. And we've got some observations from Sentinel that we've used to kind of go in and manually check, and it looks pretty good. So we know that we're locating water, and the amount of water that we say is in there is looking pretty reasonable. So I won't even bother, it's too fuzzy. So what you can then do is take that and track through time. And so now we have a time series. And what this time series shows you is how this particular water body is either used or naturally is filling and emptying through time. And so what you can see in this particular case is you've got a really cyclical filling and emptying regime, if you will. And this information is really useful, firstly for for water accounting, for understanding how people are using water, but also if this is a natural water body, for knowing when it fills and when it empties. And if this little black line was just my attempt at trying to correlate it with rainfall. So this is a very crude attempt, because this is still something in development, of trying to work out if the filling events were happening when there was a natural rainfall event. So that's another piece of information we can pull in. Once you have a time series, you can start to do all these really awesome things. So for this particular water body, we know that it's man-made, or we believe that it's man-made, because we can see the year that it was built. So we can start doing automatic processing on these time series to pull out information like the year it was built. And if we want to, we can develop a flagging system to see when it's filling and emptying. That was just a super quick snapshot of what we're doing. All of our code is available if you wanted to replicate what we're doing, and the products that I've shown are available on National Map. And I have heaps of time for questions, so hit me.